Now we are going to calculate an electric field for conducting plane. What we mean by conducting plane, the charge on conducting plane go to the surface. Let's say we have a uniform density and this conducting plane is charged positively with sigma. This sigma is in coulomb per meter squared. The objective is to find an electric field somewhere here, a distance d from this plane, and this plane is conducting with is infinite plane, means this distance compared to the length of the plane is very small. Now for this we are going to use Gauss's law to solve this problem. I will choose a Gaussian surface. We consider this Gaussian surface, we consider cylinder. So this cylinder, it will go cross. When we cross the surface, we will have this cross section. When we go, now what we will see something like that. This point is this. Then when we go through the surface, we will see this. Through the charge we see, we will have this cross section area of charges. Then we go inside, here, and then we get out. So this is what we will see. Like we get the cut, cylindrical cut on this infinite plane. Now we need to find the electric flux of this Gaussian cylinder. First we need to know how many areas do we have, an electric field through electric field directions, and then the flux in each area. So the total flux will allow us to find the electric field. Say this area, I call it 1. This area, I call it lateral area of this side, I call it 2. And then this area, remember this lateral area goes until the extreme side of this. So the other area, this another lateral area, call it 3. But remember we have the last base here, which is 4. We call it 4. This base 4. Once I found the electric flux of each area, the sum of this electric flux is the total electric flux. Now we are going to use Gauss's law. The total electric flux, it will be the flux from the area 1, it will be the integral E d1 dE1 plus the d area 2, the blue area, plus the lateral area, the yellow area 3, E d area 3, plus the flux produced at the area 4, which is E dA4. Now, before we go do any calculations, we need to find the normal, because remember this is our vectors. A, dA are vectors. If this vector A, dA are perpendicular, means the cosine of the angle between them is 90. The cosine of 90 is 0. That means if you find the electric field is perpendicular to the normal, to the surface, your electric flux is 0. Now let's start with area 1. The normal of the area 1 is this is the perpendicular to the area 1 and out. Now I call it N1. The direction of our electric field E is in the same direction as the area 1. So this electric flux E dA1, it will be is by definition is A dA1 cosine of theta. theta 1. The theta 1 is the angle between the vector dA to the angle between the vector dA and electric field. And this angle is 0. Cosine of 0 is 1. So our electric ADA vector will be just ADA 1. Okay, we said ADA1 equals ADA1. Okay, now look to the second area, the blue area 2. The normal to this area 2 is N2. Also, we said, remember, the dA2 is the area 2 times the normal to this area 2, which is the vector perpendicular to the area and outward. So what do we see this the electric field, because the electric field is going from these charges out and is perpendicular to this N2. That means the flux, there is no flux in this lateral area 2. For the area 3, there is no charge because we have conducting surface. The charges are only on the surface. If we go below the surface, there is no charges. This electric flux is 0. The same thing for the area 4. There is no electric flux because there is no charge. Our electric flux is 0. Now, the only electric flux I have is the one that is on this surface area 1. So the total flux will be just the integral A dA1, which is just integral A dA1, which is Q enclosed over epsilon 0. This Q enclosed is just sigma times the area. Now, the electric field will be constant because the density is uniform. Any position from this area, or my electric field will be constant because the density is uniform. The electric field integral of dA equals sigma A. So, let's clean this and continue here. So, we said our electric field times the integral of this area, it will be just the total area. If the integral of this Gaussian area, if I integrate it on the whole plane, it will be just the total area. And this is equals to sigma times total area over epsilon 0. This is over epsilon 0. So if I cancel this, the electric field will be just sigma over epsilon 0 if we have conducting plane. So to find the electric field just in the front of conducting plane or any point far from conducting plane, the electric field will be sigma over epsilon 0.